All right, now I want you to give this a go yourself. And so I'm giving you two half cells, one with copper going into copper sulfate and the other one aluminum and aluminum nitrate. So we're going to connect them, write out your half reactions, the overall net cell reaction, how many electrons are transferred, and the cell diagram. So give that a go yourself and then come back. Okay, so we know that aluminum is oxidized, so it's losing electrons. So what am I going to do? I'm going to go Al solid going to Al. Let's see, what is the charge on this? Well, if I bring that 3 up here, Al 3 plus is what I'm becoming, and that's aqueous. And then plus, so I'm losing those 3 electrons. That tells me that the copper is being reduced. Reduction is gain. So I'm going to start off with sulfate is a 2 minus charge ion. So that means that I'm going to have Cu2 plus because there's just one of them. Aqueous. And then plus 2 electrons going to solid copper. Now, as far as who's being oxidized and who's being reduced, well, we know that. And then for our cell diagram, what do? Remember, we can go, let's see, who's starting off at the solid? That goes on the outside. So here's my aluminum solid going to Al3 plus, aqueous. Here's my salt bridge, and then to my Cu2 plus ions, aqueous, forming up on the metal on the other side to form copper solid. So that's actually the easiest part to start off with. This one now, to write the overall net reaction, remember what we need to do is make sure that I'm electrically balanced as well as mass balanced. So if I do this, I have 2 electrons on this one, 3 electrons on this one. So I need to have a common factor. So they have to have the same amount of electrons lost as gained. So I'm just going to multiply by 2 here and multiply by 3 here. So what am I going to have? My overall reaction then is going to be 2 Al solid plus 3 of my copper. That is a U, not a C. 3 of my copper 2 plus ions, aqueous, going to, let's see, whoop, yeah, I did that. Going to 2 Al3 plus, aqueous, plus, now my copper solid, and I need to multiply that by 3. So what have we done? Right, what are the half reactions? Boom, we have those. Overall net reaction, that's that. How many electrons are transferred in the overall reaction? Well, let's see, what do we have? We have 6 electrons. So 6 electrons gained and lost. And we've answered it all. So this is really bringing everything back in to use that we've built up to this point. Now let's talk in terms of energy. And all of us go with the water example because for electron movement, I have to have potential. And the reason why we like the waterfall is you can kind of think in terms of if I have a 1-inch waterfall, it's more like a small little trickle, right? But if I have this huge difference of height for the water to travel, I have a bigger potential. And in physics terms, I like to use the high dive versus no dive, right? So if I'm on the high dive, I can be going really fast when I hit the water. If I'm standing on the pool's edge and just step off and the water's only like that far, I'm only going to be going like a little bit fast, like not very fast at all. And if I'm in the water and I step off, not well, other than I have to swim now, I'm not gaining any velocity, any speed going from one platform to the other because I'm already in the water. So what do we need? We need this potential difference. I need something to help drive that attraction repulsion, right? So remember, the electrons only have so much space that they can spread out to minimize the amount of repulsion between those charges. So I have to have a potential for them to move. Otherwise, they just won't do anything. So we define the work that can be done in terms of how much flows and the potential difference between the two. The charge flowing you can think of in terms of, well, I'm not going to get any work from a cell. I was getting ready to do physics on you. I'm not going to. I can't do any work in a cell if there's no movement of electrons. And the potential difference then would be like that height difference. So the potential difference you can actually think of in terms of your batteries. If you have a 9-volt battery, you have more potential difference than if you have a 5-volt battery. That allows for more work to be done. So let's see how we can apply that. When we have an actual cell, we have this, we define work for the energy that it can be done. So remember, work is a force over a distance. So we're using electrostatic forces. So a charge being exposed to an electric field is actually what's happening. But for our purposes, you can think of it just in terms of the work is this force times the ability to generate the potential. So the difference between a 10-volt battery and a 3-volt battery, right? So I can get more work for the more potential difference I have. And then N is just the number of moles transferred. So you can think of that as like the current. When I plug something in, I have current going. Well, this is just looking at the amount, the moles of electrons that are going to flow in that wire. And then the amount of force per charge, the amount of force of charge per mole of electrons. Well, let's see. I'm going to write this down just for those that have done physics. All this is doing is restating this. Q2 over R squared. Again, never going to have you use this, but for many folks, this just helps kind of bring this into, make it clearer if you've done the physics. So then the work, then, what are we saying that's going to be this electrostatic force thing going on here times some distance that it's traveling, right? All we're doing is defining this now in terms of the amount of electrons, the amount of charge per mole of electrons, and then the electrostatics, or the E potential of the cell. To simplify things, so this thing here, by the way, that is just the amount of coulombs per mole available for all those electrons. So each electron has this teeny, very, very tiny amount of charge available to it. It's like 10 to the negative 19, I believe. So we have to have a whole bunch of them to do anything. One electron really isn't going to do anything for us. We can do math in terms of tables. You're going to be very excited because right now I know that some of you are rather terrified. You're looking at this and you're thinking, oh my goodness, I'm going to have to do like physics stuff, and you're going to see, nope, we're going to pull from tables. So we can define the E of the cell in terms of our anode and cathode, or reduction and oxidation. So let's just kind of see how that looks. Actually, I'm going to come back to that. For my standard potentials, I have this handy dandy table. I want this bigger, so you can actually see it. I have this table. So for all those half reactions we've been doing, there's actually pre-recorded values, and those are the things that we're going to use. You're just going to look up on a table to see what their standard cell potential is. So this value here is what we're going to use. And those negative and positives just tell you more or less how favorable is it for something. Is it more likely to be oxidized? Is that its most favorable energetic state? Or is it more likely to be reduced? Is that its more favorable energetic state? So what happens to this if I put in, I don't know, my E cell is like 5-gallon buckets? Do you think it's going to go up, down, or nothing? And the answer is nothing, right? So I have this amount of cell potential per half reaction. This is not changing. This is not based on a quantity. this is how much energy I have for that 1/2 reaction. So what is going to change if I put them in 5-gallon buckets is that I'm going to have something that can last longer, right? So my battery is going to be able to go on. This is the max amount of potential that I can get from my different half reactions. And we are going to use this cell, or this chart, for a lot. You're going to see. Now let me go back to the one thing I skipped over. Oops, let's make this smaller. There we go. So one of the ways that we can relate our work is to think in terms of Gibbs free energy. If you remember, I don't remember if that's first or second quarter of chemistry, this is energy available to do work. Energy available. Let's just think about that. Available. If I can spell. So from the other slide, we saw that we can define the work in terms of the force per charge, the number of charges experiencing that, and then the electric potential. So the ability to do work here is this delta G. And if, let's see, do you remember, I might not remember, for something to be spontaneous, a negative sign for delta G means it's spontaneous. In 161 or 162, you define that in terms of enthalpy and entropy, where we said, you know, here's my enthalpy, delta H, plus my, I just forgot about my entropy, my delta S. Yeah, I'm trying to remember if there's a natural log in there. It's like 1/2 or something like that. But what we decided in that quarter was that if I'm losing energy, this thing becomes negative, right? So something is exothermic. I have a negative delta H, and entropy is kind of the magnitude of energetically available states. So something that is increasing in entropy has a positive value. Oh, so this is minus. There we go. I knew I had that wrong. So something that is increasing in entropy is going to have a positive value, meaning more availability for states, and something that is decreasing, becoming more ordered, going to a solid is the way we talked about it in 162, I think it is. That I have to do something. I have to take energy out of the system in order for a liquid to become a solid. That's all this is saying. So the same thing goes for here. Still applies. That for this to be a spontaneous value, I need a negative number. Well, I have the negative here. So if my overall E for the cell is positive, then I have something that is spontaneous. If I have an E that is negative, well, it's going to cancel out that negative sign, meaning that it's not spontaneous. In other words, I would have to plug it in and force it to go to make it happen. So my negative G, or my delta G, needs to be positive. So the fun part here, though, I want to emphasize, this is what we have been doing all gosh darn quarter. There's K. That's an equilibrium constant. So the fun thing on this is that I can use my cell potentials to figure out what my equilibrium constant is. Because I'll know the temperature. This is just the gas law. And so if I know the amount of energy or work available to be done, so if I've solved it over here, I can rewrite this thing as negative NF E cell equals negative RT ln of K. Cool. And then, you know, negatives cancel, and then I can go, let's see, so NF E cell divided by RT is going to equal ln of K. And then how do I make a natural log go away? I exponentiate both sides, so I end up with E to the NF E cell, dropped an L, divided by RT will give me my K. Boom. So with that now, we have our equilibrium constants that we can use to apply to however we want. For the purpose of this course, because this is sadly is our last week, um, just knowing how to solve for this so you can get to our equilibrium constant is all we're going to get to. So we did this one. Now let me make this smaller. And I'm going to do one more video where we calculate the sign or calculate the amount of potential available.